Okay, so let's see where we are so far. We're following the plan, all right? So, okay. So today's election day, by the way. Today is Tuesday, November 3rd, all right? Week 12. And we're going to finish chapter 5 on the tree identities, all right? On my website, I should have the a handout with the various intermediate identities. That should be on my website, all right? Otherwise, maybe remind me to email it to you, but it is on my website, the list of identities. I believe it's in my main notes also. Should be in my main notes. Okay, and also we'll start chapter 6 on the law of sines and law of cosines. We'll finish chapter 6 later this week. Then the homework is due Friday of next week, November 13th. All right, chapters 5 and 6. All right, and we'll start the last block next Tuesday, 7 through 10. Okay, so any questions thus far? Any questions thus far? Oh, well, but we need some people to staff juries, right? Really? Yeah. Wow, I'd like some more information. Oh, okay. Yeah, I'd like some more information, please. Okay. I mean, I didn't know if there was a way to do it by Zoom or something, but I'm glad I mentioned that I had jury duty Friday because I was wondering how that was going to work out. I don't know if there's a link that your friend could provide, like a news link. Oh, okay. Yeah, I wonder if I can get a link to that. I'll check for that. Okay, thank you very much, though. That would save me a trip, definitely. I'd appreciate that. So any other great advice or questions before we start? Any other great advice? All right, so we're recording, all right. So let's go on. All right, so my list is different from yours, the playlist. Okay, so it's over here. Okay, we're on day 23. Oh, and by the way, I wanted to mention that I had office hours on Monday, and a student was generous enough to let me record the session. So I wanted to note that on Monday, I'll put this in chat. On Monday, or do I want to, you know what, maybe I'll put it here in the, so the video can catch it. So in office hours, I had an office hour session, which I have posted on YouTube. And we covered, what was it? 5.1, number 2, A and F, on some simplifications. And I did B in an after class video. That was in the video after class. Again, the student was generous enough to let me record it. And then 5.2, number 1B, C, D. Again, that was in the office hour session I posted on YouTube. So again, thank you to the generosity of the student. And I have nice video stuff on that on YouTube. And 5.B is part of the class video after class. All right, any questions before we go on? Any questions? Okay, so refer back to the video to catch which these were. All right, so we're going to start off now. That was a reminder, right? Let's start off now. And go ahead and put questions in chat.
Or figure out 19 identities.
Okay, let me start it again. Okay, here we go.
Hi, everyone. In sections 5.4 and 5.5, you will need to be able to know or figure out 19 identities and be able to use 8 more once you see them. So 19 plus 8, in a way, 27 more. In fact, you should be able to recognize pieces of these identities over here so that you can recognize when you can apply them and realize, hey, I might be able to use an identity here. So you should be familiar with the various pieces in here. Ideally, you would memorize them, but it also helps to be able to figure them out. And also, it helps to recognize various pieces in here. So let's start applying these identities. First off, we can do things like find the exact value of something like sine of 15 degrees. Because we can rewrite 15 degrees in terms of other known special angles. In many of these problems, it may be easier to work in terms of degrees. You could use radians, but remember that it's sometimes hard to apply arithmetic to radian measures, like pi over 4 or pi over 3. Students often have a hard time adding or subtracting fractions with pi in them. I hope you can do that, but you may find that in many of these problems, it will be easier to work in degree measure, like 15 degrees. Okay, so how can we rewrite or re-express 15 degrees in terms of other known special angles? There are actually infinitely many ways to relate this 15 degrees to known special angles, but what are a couple of ways that we can rewrite 15 degrees in terms of known special angles? Well, let's see. 15 degrees is equal to how many degrees minus how many degrees? There are infinitely many pairs of responses you could give, but 15 degrees is equal to how many degrees minus how many degrees? What would be some simple responses here? Well, again, there are infinitely many possible choices you could make, but you could say 15 degrees is equal to 45 degrees minus 30 degrees. You could also do, for example, 60 degrees minus 45 degrees, but let's go ahead and run with this. Which implies that we might be able to use a difference identity because of the subtraction there. So we're going to express sine of 15 degrees as sine of the quantity 45 degrees minus 30 degrees, this difference of two special angles. Now remember, does this equal sine of 45 degrees minus sine of 30 degrees? And the answer is nope. Cross this out. In fact, I'm going to erase it. That's wrong. We do not have what we call linearity here, or we don't have a distributive property here. Remember, there's an actual difference identity. That's more complicated than that. It might help to perform a substitution. You could do this mentally. We could let we could let 45 degrees be u, let 30 degrees be v. And from the handout we got earlier, well, by now, I hope you know this, but sine of u minus v is equal to, I'll put in some parentheses to make this clearer, sine of u times cosine of v minus cosine of u times sine of v. Remember, the sum identity was the sum of the mixed up products. The difference identity means that we switch the plus sign here to a minus sign. So let's apply this difference identity. Again, sine of u minus v equals sine of u, 45 degrees, times cosine of v, 30 degrees, minus cosine of u, 45 degrees, sine of v, 30 degrees. And hopefully you won't need a calculator for these. In fact, you should write down exact values anyway. What was the deal for the 45 degree angle? Well, both the sine and the cosine values were root 2 over 2. Those were the coordinates of that intersection point. Both the cosine value and the sine value for the 45 degree angle will be root 2 over 2. That's for 45 degrees. And for 30 degrees, you could get this from a table that you've mind dumped on your test, like on the back of the test. 30 degrees, that was the sort of flattish angle, not that flat. 30 degrees was kind of the flattish angle. Low and to the right. Low y coordinate, low sine value, that was 1/2. You could say 1/2 is not that low, but it's a lot lower than the x coordinate, the cosine value, which is root 3 over 2. Or you could get these from a table that or a big unit circle, or a quadrant of the unit circle, that a quarter of the unit circle that you've mind dumped on the back of your test. Anyway, These are known special values. Both the sine and the cosine of 45 degrees is root 2 over 2. Cosine, whoops. Again, this is cosine, this is sine, technically. Cosine of 45 degrees is root 2 over 2. Sine of 45 degrees is root 2 over 2 also. Now in red, the cosine of 30 degrees is root 3 over 2, and the sine of 30 degrees is 1/2. So you should write out these special values. Exactly. With a calculator, you might get decimal approximations, but we want the exact answer. This should be fair for a non-calculator part of an exam. Remember that fractions multiply across. What is root 2 times root 3? That is root 6. We get root 6 over, of course, 2 times 2 is 4, minus root 2 times 1 is root 2. 2 times 2 is 4 again. We have like fractions. We should combine these. We're combining like fractions. On the top, we have root 6 minus root 2 all over 4. Question, is root 6 minus root 2 equal to root 4? Is the difference of roots equal to the root of the difference? The answer, generally no. And in this case, no, absolutely not. This is not 2. So that's wrong. Do not be tempted. That is not root 4 up there. I want you to simplify, but only in correct ways. That is incorrect. I'm going to erase all this. Leave this be. That's about as good as we can get it. Some books actually factor out a root 2 on top, but we're good with it. So then if you do that, you would get root 2 times the quantity. When you factor, you divide. We're back to, in fact, you could get it from here up here, root 3 minus 1 all over the 4. Some books actually prefer that form. I will accept this form also, though. Root 6 minus root 2 all over 4. And if you have a calculator, you can do a decimal approximation for that. On some exams, you might be asked to give both an exact form and an approximation. Okay, do not go any further. Remember, root 6 minus root 2 is not root 4. So that's one way of getting an exact form, the exact value for sine of 15 degrees. But there's another way we can do this. What's another way that we can look at 15 degrees? Okay, we can think of it as a difference of a pair of special angles, like 45 degrees and then minus 30 degrees. But there's another way to look at this. 15 degrees. I'll type this out. "15 degrees is half of what?"
Didn't get that.
Whoops.
Could you try again?
Oh, come on, we can get this. Please be quiet, Siri. Oh. So 50 degrees equals 1/2 of what? 30 degrees. Okay, 15 degrees is half of 30 degrees. Half of 30 degrees. We may be able to use a half angle identity. Okay, so sine of 15 degrees is sine of half of 30 degrees. So we can use a half angle identity where theta is 30 degrees. Using this identity over here, where theta is 30 degrees. So applying the identity, we get plus or minus the square root of 1 minus cosine of theta, which is twice the 15 degrees, right? So cosine of 30 degrees all over 2. And by the way, early on we can figure out, hey, the sine of 15 degrees, we know that 15 degrees is a quadrant 1 angle. So what sine, positive or negative, is this sine value? Well, in quadrant 1, we know that all trig values are positive. We know that we can take the positive root here, which means I can delete this basically. What is the cosine of 30 degrees? We already figured that out in the previous method. Cosine of 30 degrees was root 3 over 2. But now we don't like the fact that we have a compound fraction in there. And also, we'd like to rationalize the denominator. So let's multiply by 2 over 2. We're multiplying by 1 here. When we do that, and we distribute through the top, 2 times 1 is 2, minus this fraction times 2 is root 3, all over 2 times 2 is 4. Again, we can delete the plus minus symbol at this point. We know that this will be positive. The sine of 15 degrees is positive. Okay, now down here, remember that we do have a rule for radicals. This does work. The square root of a over b, assuming these are both positive, is equal to the square root of a over the square root of b. The square root of 4 down there is going to be 2. Again, we can remove the plus minus, and we can get this as our final answer. So I'm claiming that this is another form for the sine of 15 degrees. Now you might be going, well, wait a minute, that doesn't look like what we got last time from method 1 when we applied a difference identity. Well, that could be okay. It's often the case, in trig especially, that you might get one form of the answer, your friend, or at least your study buddy, gets another form for the answer, and you could both be correct. In fact, on an exam, I would accept both of these responses. Some people might prefer this because you don't have the nested radicals, but if you come up with this on an exam, let's say, then I would accept this as well. In fact, these are equivalent. As an exercise for you, you might convince yourself that these are equivalent if you square this, and you'll find the squares are equal. And since you know that sine of 15 degrees is positive, that's a very good sign, literally. Okay, take the square of this, take the square of this, show that those are equal, and that should be pretty convincing. All right, so we're going to do some more evaluating. We've evaluated sine of 15 degrees here, and simplifying in later videos.
Okay, any questions before we proceed? We're applying these advanced identities. Any questions before we proceed? Okay, feel free to put questions in chat.
Hi, everyone. Like I said in the previous videos, it helps to be familiar with these identities over here and their various pieces. Now, it may also be helpful to mind dump these early on in an exam. By a mind dump, I mean you write them out quickly on some scratch paper or on the back of your test. That's not cheating, assuming that you have gotten the test already and the instructor says you can start. So let's see if you can recognize this form here. Imagine a substitution, like a snap substitution. Tangent of 25 degrees, let's say that's u, plus tangent of 20 degrees, let's say that's v, all over 1 minus tangent of 25 degrees, or u, times tangent of 20 degrees, or v. Now, does this sound familiar? Tangent of u plus tangent of v, all over 1 minus tangent of u, tangent of v. That sounds to me like the sum over 1 minus the product. And I hope that sounds familiar. That's going to be overall a sum identity for tangent. So here's the identity that we're using. Tangent of u plus v equals the sum, tangent of u plus tangent of v, over 1 minus tangent of u, tangent of v. And this identity will help us because all the way up here, we don't know the exact values of tangent of 25 degrees and tangent of 20 degrees. I know these values are positive. I know that this is bigger than that. And I know that they're going to be less than the tangent of 30 degrees, say, but I don't know their exact values. It turns out the sum identity will help us. And we're actually applying this identity from right to left. That's why I'm telling you that it's important to be able to recognize when an identity might be useful, or at least be prepared to look over the list of identities you've mind dumped on your exam. So when you see this, especially if you think of a snap substitution, well, think about this form and you might realize, aha, this is the right-hand side for the sum identity for tangent. So let's apply this identity backwards, right to left. In fact, I'll write it in reverse. All right, well, U was 25 degrees. V was 20 degrees. Okay, same for down here. And you can see here that when we do that, I'm just rewriting the given expression over here, right? So if you want to call this thing star, right, I'm basically telling you that star is equal to tangent of 25 degrees plus 20 degrees. U is 25 degrees, V is 20 degrees. Okay, so what is U plus V? What is 25 degrees plus 20 degrees? It is 45 degrees. And I hope you know, either from the unit circle or a table, that when you consider the 45-degree angle, the slope of this terminal side is 1. The tangent of 45 degrees is 1. That's a great special fact. So all of this big old mess over here, it turns out to be 1. In fact, your calculator might be a little bit off. Your calculator might say something like 0.9999 whatever because of rounding error. Actually, this is exactly 1, right on the dot. This is great for a placement exam problem. This is the kind of problem they love to put on a placement exam. Like if you're entering university, great problem they would put on a placement exam. Okay. Now let's simplify a more general trig expression in theta. Simplify 1 over sine of 3 theta cosine of 3 theta. And actually, I'm going to show you a solution that's probably clearer than what I have in my notes. So it's good to attend lecture. Let's take a look at this. Let's perform a substitution because we have these matching pieces over here. Let's let U be 3 theta. Then we can rewrite this as 1 over sine of U cosine of U. Right off the bat, this looks more comforting to us. And let's look at the bottom here. Well, you might look at this and you might go, well, I guess I could rewrite this as cosecant of U, secant of U. That's true, but we're going to try to get something more compact. Look down here, sine of U, cosine of U. What trig identity has that as a major part of it? In fact, let's try to go to our list of identities here. Let's see, the product. Sine of U times cosine of U. Look at these right-hand sides, a product. Sine of U times cosine of U, almost all alone, maybe, look at this here, interesting. Sine of 2U equals 2 sine of U cosine of U. Some students might say, but hey, there's a 2 in front, I can't use this. Well, you might be able to do some massaging, do some modifications. We can try to use this. In my notes, I use the fact that sine of U cosine of U is 1/2 sine of 2U. That's one way of looking at it. But here, I'm going to try a different approach. I will use this double angle identity for sine, right? It's the double angle identity for sine. Let's use this, but in a different way. Okay, so in order to apply the identity, it would be very helpful if I had a 2 in front of sine of U cosine of U in the bottom, the denominator. Well, let's go ahead and insert a 2 as a factor. But wait, you can't just put in pieces because you feel like it. You have to pay for them somehow. Is there an easy way to pay for multiplying the bottom by 2? Well, yes, there is. Multiply the top by 2. And that is legal because all we're doing is multiplying by 1. We're basically multiplying by 2 over 2. And again, we want to multiply by 2 down here because then we're going to make the bottom look more like a part of a known identity. What is 2 sine of U cosine of U? It's the right-hand side of our trig identity, this double angle identity over here. So I can substitute 2 sine of U cosine of U outright by sine of 2U. We get the 2 on top over, the bottom then becomes, much more simply, sine of 2U. And we've really shrunk this thing down. But we're not done yet. there are a couple more things we can do. First of all, we try to avoid fractions where possible. So what is the reciprocal of sine of 2u? As far as the 2 goes, remember the 2 we can pop out in front. Remember, it is legal to pop a factor of the top out on the outside. If the 2 are on the bottom, we'd have to pop out a 1/2. But the 2 is on top, so we can pop it out, and then a 1 is left on top here. Do not forget the 1 up here. I should put this in red. When the 2 pops out, it does leave behind a 1. Okay, you still have a fraction here. Now, what is the reciprocal of sine of 2u? It is not secant of 2u, it's cosecant of 2u. So we've made this look a lot nicer. 2 cosecant of 2u. But wait, are we done? Are we done? This looks very nice, but remember, it's in terms of u. And u is our creation. It was used to help us out. But the given expression was in theta. So if your friend gives you an expression and tells you to simplify it, and you leave this thing in u, your friend's going to ask, well, what the heck is u? U is 3 theta. You better plug that back in. Substitute back. U was 3 theta. And then in the argument here for cosecant, what is twice 3 theta? Remember, it's a double angle identity. Well, here, right, and then we move over here. We have cosecant of 2u. Okay, cosecant of twice 3 theta. Twice 3 theta is 6 theta. And you can delete the dot there. 2 cosecant of 6 theta, that looks very good. You really couldn't do any better than that for this expression. So that big ugly thing at the beginning, 1 over sine of 3 theta cosine of 3 theta. For example, in calculus, you'd be very irritated if you had to take the derivative or integral of this. But if you simplify this down to here, okay, this is much easier to differentiate, that is, take the derivative of or integrate. 2 cosecant of 6 theta. Remember, simplifying can really be your friend in both pre-calculus and in calculus. Simplification is often your friend. You help yourself by rewriting this ugly thing as 2 cosecant of 6 theta. So I think that's a clearer way of expressing the solution. Now, in my notes, my solution is correct, but I think it's harder. So for example, here I tell people, okay, recognize you have a double angle identity in play, right? If we had a 2 in front, we'd have sine of 6 theta, right? Twice 3 theta. And then if you were to divide both sides by 2, basically what I'm doing here, I'm adopting the strategy of solving for this thing in here. I want to actively substitute that. And I substitute it by 1/2 sine of 6 theta. When you do that, the reciprocal of 1/2 is 2. The reciprocal of sine of 6 theta is cosecant of 6 theta, which we got before, right? And this solution works, but I think it's harder because then here I didn't really use a substitution very well. I could have let u be 3 theta. And I think this is kind of harder to understand. Whereas my method that I just showed you, okay, which involved making something look like the form you want to see, right? So you're kind of engaging in wishful thinking. It's okay to engage in wishful thinking if you compensate, if you pay for it appropriately. Here, it's okay to compensate. It's okay to pay for multiplying the bottom by 2 if you do what? If you multiply the top by 2. That's legal. So that's a case where wishful thinking can be made legitimate if you compensate or pay for this accordingly in a legitimate way. But make sure it's legitimate. For example, you could not add 2 to the top and the bottom. That's not a legal move. You can, however, multiply the top and the bottom by 2. That's like a compensation idea. We talked about this in, I believe, 0.10. Make something look like the way you want it to look. We can apply the identity immediately. You pay for what you did. Next up, oh, well, before we start solving equations, a comment. In chapter 4, I had you look at identities like these, where you look at something like this, right? And you consider the unit circle. Consider the unit circle. Assume for now that theta is acute. Although you can run an animation in your head and imagine theta changing. If theta is in quadrant 1, where's theta plus pi? What quadrant's that in? Theta plus pi is in quadrant 3. Now, how does the sine of theta plus pi, how does the sine value for this angle correspond to the relate to the sine value for this angle? Are they equal, opposites? What are they? Sine of theta plus pi versus sine of theta. How do the y coordinates, sine value is y coordinate, remember? On the unit circle. The sine value is the y coordinate on the unit circle. How does the y coordinate of this point compare to the y coordinate of this point? In fact, even if you change theta, theta could be any real number of radians. If you consider the sine of theta versus the sine of theta plus pi, how are the sine values always related? They are always opposites. For example, these y coordinates here are opposites. The sine of theta plus pi is the opposite of sine of theta. So you may have conjectured something like that based on chapter 4. But now in chapter 5, guess what? We can verify this. We can prove this conjecture and make it a bona fide theorem. By using what identity? The sum identity for sine. Try it out. Try it out. And you'll see stuff like this on the homework. It falls through very quickly, meaning it works out very quickly. Next up, we're going to solve equations using these additional identities.
First off, any questions? Any questions? Feel free to put questions in chat. All right. So about 20 minutes on trig equations. All right, coming up. All right, questions in chat.
Hi, everyone. Let's go ahead and solve a trig equation using our new toys, our new tools, these additional trig identities. Let's solve sine of x minus cosine of 2x equals 0. Now, don't do anything foolish like taking out that 2. Don't engage in wishful thinking. We're going to apply an identity, a double angle identity for cosine. Now, the way that some students might approach this, and then I'll show you a more efficient and concise way. The way some students might approach this is, well, let's see, cosine of 2x, yeah, I remember that. The cosines minus the sines. The cosines minus the sines. Cosine of 2u was cosine squared of u minus sine squared of u. And you could try that. Please remember what? When you put in that expression, when you substitute in cosine squared of x minus sine squared of x, first of all, it's an x, not u. But more importantly, grouping symbols. Remember, whenever you perform a substitution, be prepared to put grouping symbols, especially when there's a minus sign in front. If there's a plus sign in front, then this isn't such a big deal. But if there's a minus sign in front, oh yeah, we're going to need grouping symbols. Or distribute directly, but I'd recommend grouping symbols. Then we can distribute the -1 in here. Sine of x minus cosine squared of x, again, plus sine squared of x. You've flipped the sign there, equals 0. And then you go, well, wait a minute. One of these things does not look like these others on the left side. How can we make cosine squared of x look more like sine squared of x? Well, Mr. Pythagoras. And again, grouping symbols would help. Cosine squared of x is what? From Mr. Pythagoras, a Pythagorean identity, it's 1 minus sine squared of x. But since it's more than one term here, and since we're following a minus sign, we need these grouping symbols. We distribute sine of x minus 1 plus, it's a plus, sine squared of x plus sine squared of x equals 0. Over here, what's apple plus apple? Or what's u plus u? It's twice apple, or 2u. 2 sine squared of x, and then plus sine of x, and then minus 1 equals 0. And we have here a nice quadratic in sine of x. So that's the way that a lot of students would approach it, but there's actually a more efficient way of getting this. I'll go back up to here. Cosine of 2x. Remember, we had 3 double angle identities for cosine of 2x. So if you're able to figure them out, or if you've mind dumped them, which one would work best? We have 2 other identities that could work. And I think we could use the one with sine squared of u here. So instead of this big daddy identity here, let's use cosine of 2u equals 1 minus 2 sine squared of u, where we're basically doing our Pythagorean work already. This already incorporates some of the Pythagorean work we did in here. So instead of basically rederiving this, hopefully you can remember this or get this from your mind dump sheet and apply it directly. So then if you do that, you would get sine of x minus the quantity. Again, we need grouping symbols here. Instead of cosine of 2x, let's use 1 minus 2 sine squared of x. 1 minus 2 sine squared of x. I'll write the 2 in here. And then when you distribute the negative 1, you get sine of x minus 1 plus 2 sine squared of x. And then when you combine this stuff with the sine of x, remember just the sine of x is the other piece here. When you combine these pieces, right? So we get, no, we didn't have to combine. I already combined the sine of x piece. Okay, so we combined the sine of x with this stuff over here, right? Okay, but we already put in the sine of x here. All right, so the left-hand side becomes 2 sine squared of x plus sine of x minus 1. Okay, exactly what we got over here. But this is more efficient if you use the more appropriate identity right off the bat. So on the one hand, even though this might seem more immediate, then you have to actually do some more work and you kind of rederive this structure along the way. So it takes more steps. Whereas if you strategize and if you realize which identity would really work best, if you can get that best identity, then your work goes a bit faster. But on homework or exam, I'd accept either approach. Now at this point, a substitution might be appropriate. You don't have to do a substitution. I don't in my notes, but we can do a substitution. Let u be sine of x. And then we can get a quadratic in u. All right, so we apply the substitution. Again, here I didn't apply it. You can go ahead and factor this directly. You don't have to do a substitution, but I think people might recognize this better. 2u squared plus u minus 1, 0. We have a square here. And we can factor this old school. We can factor it as 2u minus 1 and u plus 1 and equals 0. Of course, in order to apply the zero factor property, we have to isolate 0 on the right side. We have a zero factor property. If you're going to use a factoring method, we ultimately need a 0 on one side here. Right. So 2u minus 1, or subbing back, 2 sine of x minus 1, and then this factor, u plus 1, or sine of x plus 1. So if you do a substitution, then you would go to here as your next step, or instead of going to here, you could solve for u directly over here, right? So we can get our two cases. 2u minus 1 equals 0. You add 1 to both sides. and then divide by 2, and we get u equals 1/2. So again, here I set 2u minus 1 equal to 0, right? Add 1 to both sides, we get 2u equals 1, divide both sides by 2, u equals 1/2. And that's going to lead to case 1. I'll put this in red. And then over here, u plus 1 equals 0. Well, that's pretty straightforward. U plus 1 equals 0. Subtract 1 from both sides, u equals -1. So we need sine of x to be -1. That's case 2. I'll put that in blue. All right. So you can either substitute and solve for u directly, or don't bother substituting. Just factor directly in terms of sine of x. Set each factor equal to 0 and solve for sine of x, which is like solving for u here and here. Either way, we get 2 cases. One case where sine of x is 1/2, and one case where sine of x is -1. And again, you could do it either way. You can either do it through a substitution or just factor directly in terms of sine of x. But either way, these are going to be our 2 cases. We're going to solve these 2 smaller trig equations, but don't go too fast. Take a step back and think these through. Well, we have 2 cases. All right. Case number 1, sine of x equals 1/2. That was in red here. Sine of x equals 1/2. We're going to solve this trig equation. Don't rush. You can get this, but don't rush. I'll put this in red, since that's our color for this case. All right. First of all, we agree that 1/2 is a legitimate sine value. It's in the range of sine. It's in the closed interval from -1 to 1. In fact, it's a known special sine value. We can get exact solutions coming out of this equation. We won't have to use inverse sine or arc sine notation. We won't need decimal approximations. Okay, so, well, first of all, the arc sine of 1/2 will be a solution. The sine of what is 1/2? In quadrant 1, what's the acute reference angle here? Sine of 30 degrees is 1/2. Although here, when you're solving equations, going back to radians may be more helpful. Pi over 6, that's going to be a key solution for this equation, and more importantly, it's going to be the brother, the co-reference angle for all the solutions to this equation. So pi over 6 and all its coterminal twins will be all the solutions we need from quadrant 1. But in what other quadrant is the sine function, S-I-N-E, positive in value? Where is sine positive? In quadrant 1 and also quadrant 2. All right. And actually, this guy is kind of flat, right? Let me indicate that. He's kind of flat, right? Although the y-coordinate here is 1/2. So what's a key brother for this point? Although, as we'll see later on, it turns out that we don't even need a representative for this point. But many students would like to know what a key representative for this point is. I think many students would choose pi minus pi over 6, the supplementary angle. I think many students would choose 5 pi over 6, which is the most famous representative for that point in quadrant 2, the most famous brother in quadrant 2. So if you wanted to solve this equation individually, well, it would be, if this were the original question, the set of all x in the reals such that x equals pi over 6 plus 2 pi n, or x equals 5 pi over 6 plus 2 pi n. With the plus 2 pi n's, where n is integer, we're picking up all the coterminal twins for both these angles. So this is basically giving us all the solutions for sine of x equals 1/2. But remember, there's a second case where sine of x equals -1. So this picture is just reiterating this picture here. Again, as I'll show you later on, it turns out we didn't even have to identify the 5/6. There's a clever way of avoiding having to know this. Although you should know 5/6 is the key rep for this point. All right, off to the second factor, all right? Sine of x equals -1, basically, all right? In blue, -1 is in the range of sine. It's a sine value. And where is the corresponding point on the unit circle? Sine of x translates to the y-coordinate, the vertical coordinate. It's kind of confusing because cosine of x is actually the x-coordinate on the circle. X is an angle here, remember? X represents an angle here. For what angle is sine equal to -1? Well, there are a couple of reps we could use for this point. We could use 3π/2, the most famous positive representative, or its most famous negative coterminal twin, -π/2. I'd accept either. And I am asking for all real solutions. If I'm not saying otherwise in the problem, I want to find all real solutions. The implication is that we solve this on R. I want all real solutions. All right, so from this south pole, we get this. X equals 3π/2 or -π/2 or any coterminal twin. These are the two most popular choices. 3π/2, let's say, plus 2πn, where n is integer. We want to pick up all the coterminal twins for that south pole. Okay, so if we bring it all together, you could say the solution set could look like this. The set of all x values in the set of real numbers such that x is of the form π/6 plus 2πn. I'll remind you where these are. π/6 plus 2πn. So all the reps for that point. Or x equals 5π/6 plus 2πn. So all the reps for this point. Or x equals 3π/2 plus 2πn. All the reps for the south pole, where n is integer. And I would accept this as a final answer. However, it turns out here, there's a remarkable symmetry, which I wouldn't require you to use, but one nice result from this symmetry is that it turns out that you only need one representative for any of these points. And in fact, a rep for the south pole, like 3π/2 or -π/2, may be the most convenient and accessible. Because some students might be puzzling, wait a minute, the sine of what is 1/2? Now, I hope you can figure that out. But let's say you're stressing out, right? Really, we just have to worry about a rep for any one of these points, like this point. We could take 3π/2 or -π/2. And then we rotate. Let's draw in these radii, these line segments. I call this the peace symbol pattern. If you remember the 1960s, symbols from the 1960s peace movement. I guess we could relate this to radioactivity nowadays, but take a look and check this, work this out. A third of a revolution about the unit circle. A third of a revolution about the unit circle. A third of a revolution back to the South Pole. It turns out that we can get all real solutions for the equation by starting at any representative for any of these 3 points. 3π/2 or -π/2 could be the easiest ones to use, corresponding to South Pole, and then revolving either counterclockwise or clockwise by third revolutions. A third of a revolution, 2/3, 3/3 is one full revolution, going by thirds of a revolution. What is a third of a revolution? Well, how much is in a full revolution? A full revolution is 2π radians. What's a third of a revolution? Counterclockwise, 2π/3. So what do? Take any rep for any one of these points and add 2π/3n, where n is integer. This counts the number of third revolutions. If n is positive, we go counterclockwise. If n is 0, we stay put. If n is negative, we go clockwise. A more efficient form, the peace symbol, or the radioactivity symbol. Start at any representative for any point. A rep for the South Pole may be easiest because a lot of people might forget pi over 6, or it might take them a while to figure it out. Again, I hope you can figure it out quickly, but still, 3 pi over 2 may be easier. And you go around by third revolutions. Okay. In fact, here, if you want to have the nicest form in terms of show, pi over 6 may be the best looking, right? It may be the Brad Pitt of these angles, even though 3 pi over 2 might be easier to find. The set of all x in the reals such that x equals, you can take any rep for any point. 3 pi over 2 might be the easiest to figure out, maybe negative pi over 2, but pi over 6 is probably the nicest one to write. So in textbooks, they might use pi over 6 because it's the prettiest of them. It's the best looking, the Brad Pitt of these three. Pi over 6 plus, and then again, a third of a revolution is 2 pi over 3, n, where n is integer. N counts the number of third revolutions, and if n is negative, you go clockwise. Whoa, whoops. I made this mistake earlier. X is in the reals. The set of all x in the reals, such that n is in the set of integers. Okay, I didn't make that mistake earlier, did I? Well, I did. This is z. Okay, that's z. Okay. So be careful. The set of all x in the reals, such that n is in z, the set of integers. I've made this mistake before. So this is the most efficient form for the solution set, but I would not penalize you. I would not mark you down for not giving me the most efficient form. Okay, but give me something correct and reasonable. Something like this I would accept. It's correct and it's reasonable. Don't try to start out listing individual angles, a whole bunch of individual angles. That would not be reasonable. You'd have to use ... or something. There are infinitely many solutions. Okay. Next up, a more exotic application. Using a right triangle technique to express this strange expression algebraically. Next time.
Okay, any questions before we go on? So this next one, we'll probably, let me check this one. Yeah, we might take a break after the next one. Let's see.
Hi everyone, we're continuing with sections 5.4 and 5.5 on these additional trig identities. But first, I want to take you back to section 4.7 and this creature that we, in a way, simplified algebraically last time, or that time. Cotangent of inverse cosine of x over 3. This was an expression that mixed a basic trig function and an inverse trig function. So here, we had this mixture of functions, and we couldn't really apply the inverse properties. If this were cosine, maybe we could. But in this kind of a mix here, it helped to do a right triangle solution. Something like this. Or use related Pythagorean identities. Now, we're going to consider an expression like this. We're going to write sine of 2 arc cosine of x. The 2 here is the irritant. We're going to write this as an equivalent algebraic expression in x. Again, that's an expression we might have seen back in chapters 0, 1, or 2. In section 4.7, for example, it turned out that this expression here was equivalent to this algebraic expression down here, x over root 9 minus x squared. That's algebraic. Think of the quadratic formula and its structure. But how can we rewrite this? The 2 there is irritating. Well, let's first apply a substitution. That would help. In my solution here, I don't apply it as aggressively as I probably should have, but I'll apply it aggressively. Let's substitute. U equals arc cosine or inverse cosine of x. So basically, we're dealing with sine of 2u. sine of 2u. So you think of what identity? Well, it might be hard to read it like that. This here, the double angle identity for sine. Sine of 2u is 2 sine of u cosine of u. In fact, I would probably put that as part of my actual work. So this is sine of 2u. And sine of 2u equals this stuff over here. Okay, now, and you don't even have to sub back. We can kind of keep this in u for now, all right? But now we got to figure out, so what are sine of u and cosine of u? So if we can get expressions for sine of u and cosine of u in terms of x, remember our ultimate goal is to get an expression, an algebraic expression in x. If we can express sine of u and cosine of u in terms of x, we're really there. We're really done. Well, right off the bat, u equals r cosine of x. Or another way of looking at it, I'll turn it around and use the inverse cosine notation. Inverse cosine of x equals u. Inverse cosine of x equals u. Well, if inverse cosine of x equals u, then that means that what is true? Cosine of what is what? If inverse cosine of x is u, then cosine of u is x. Remember, when we go from a statement to its inverse version, the inverse statement, we're switching the inputs and the outputs. It's similar to what we did in section 4.7. If theta is inverse cosine of x over 3, or if this equals theta, then cosine of theta is x over 3. It was very similar to that. So cosine of u is x. Hey, wait a minute. Cosine of u is x. I know exactly what this guy is. This guy is just x. So that part comes through in a fairly straightforward fashion from here if you understand this inverting process, writing the corresponding inverse statement. It's kind of like going from a log form to an exponential form, a zigzag. Okay, anyway, cosine of u is x. So this here is x. This ugly expression, cosine of u is x. You may not want to write all this out. This looks pretty intimidating. Let's look at this. 2 sine of u cosine of u. We know cosine of u is now x. The question now becomes, what is sine of u? What is sine of u? Well, we can either use a Pythagorean identity, or it might be friendlier to use a right triangle. Remember, cosine of u is x. Another way to look at it, cosine of u is x over 1. So katoa. Cosine is adjacent over hypotenuse. So a natural model for this statement would look like this. Cosine of u, this angle here, is equal to adjacent over hypotenuse. X over 1 is x. And then how do we get this missing side length over here in terms of x? We use the Pythagorean theorem. So we could call this b, for example. Do I do the work? No, I don't do the work, but you can work this. You can work this out. I'll write this in blue. Okay. So we have x squared plus b squared. This guy we want. X squared plus b squared equals 1 squared, or just 1, right? 1 squared is 1. Don't engage in wishful thinking. Don't put the b squared alone on one side. He's buried in there. But you want to solve this for b, and it turns out that you get b equals plus or minus the square root of 1 minus x squared. And it turns out that we don't need the plus minus symbol. It works out, okay, even if u is not acute. You can remove the plus minus symbol. you can remove the plus minus symbol. It works out. You can look at various cases. But it does work out that you don't need the plus minus. So b is simply root 1 minus x squared. And that's important because now we can find out what sine of u is. Remember, that was the piece that was in a way, not missing, but we needed to express this in terms of x. We had to express sine of u in terms of x. Okay, so what is that? So katoa. So katoa, sine of u equals, from u, opposite over hypotenuse. So that's going to be b over 1. What was b? It was this guy, root 1 minus x squared. It's moved over here. 1 minus x squared over 1. 1 minus x squared over 1. Okay, root 1 minus x squared. So that goes into here. So this thing in here is going to be the quantity, or just the square root of 1 minus x squared. That goes in for sine of u. We're substituting that in. So we get 2 times that times that. We normally bring the polynomial pieces out in front to the left. So we end up with 2, we move the x over here normally, and then times the square root of 1 minus x squared. And that's algebraic. And in some ways, that's a lot nicer than the original expression over here. And in calculus 2, maybe you have to re-express this in this fashion. This might be easier to manipulate. 2x times the square root of 1 minus x squared. That's algebraic. In fact, we could even go to Desmos. All right, let's go to Desmos. Here's sine of, or what was it now? It was sine of sine of 2 arc cosine of x. Sine of 2 arc cosine of x. All right. Domain looks to be from -1 to 1. Range looks to be from -1 to 1. Okay. And I claim that this is equivalent to 2x times the square root of 1 minus x squared. Hey, look at that. I'm just recoloring the graph. Not a proof, but I'm pretty convinced these are equivalent. Not bad, huh? And this looks a lot friendlier than that in some ways. Well, there is a certain elegance to this in some ways, but this is algebraic. And these are equivalent expressions. They even have the same domain. From -1 to 1, you might be able to see that. All right. Now, sometimes in placement exams, you might see something like this. Cosine of these guys here. And remember that these inverse tangent values, we often associate them with angles. So you might call arctangent of 1 u, where u is like an angle, and arccosine of x like v, where v is like an angle. And then you can use this identity here, right? Cosine of u plus v. You use this identity, and it turns out that you can use procedures similar to what we just discussed. You can try this out. All right. Next up, we're going to look at some PRIs, which are used all the time in calculus, especially Calc 2, Math 151. Next time.
All right, are there any questions before we take a break? Any questions? All right, so let's take a break now. I have 8:10. Okay, let's reconvene at 8:21. Remember to mute. We've had problems with people video muting and audio muting, right? Okay, so over here. Okay, come back, 8:21. Remember to mute, and now remember to record. Any questions before we go on? All right. So let's go and proceed. Okay.
Hi, everyone. We're now going to apply the power-reducing identities, the PRIs, which you use all the time in calculus, especially Calculus 2, Math 151, because calculus hates squares. Calculus hates squares. It doesn't really like them for derivatives when you're differentiating, and it really doesn't like them for integration when you're integrating. So for example, let's express cosine squared of 2x. Maybe you have to integrate.
Let me start at the beginning because I know some people like the captioning. Hold on a second.
Hi, everyone. We're now going to apply the power-reducing identities, the PRIs, which you use all the time in calculus, especially Calculus 2, Math 151, because calculus hates squares. Calculus hates squares. It doesn't really like them for derivatives when you're differentiating, and it really doesn't like them for integration when you're integrating. So for example, let's express cosine squared of 2x. Maybe you have to integrate this in Calc 2. Express cosine squared of 2x in terms of first powers of cosines. What? Well, I might frame it like this. Rewrite this expression in such a way that you can fill in these boxes with real numbers. So express cosine squared of 2x as potentially a real number plus or minus a real number times cosine of a real number times x. Something like that. Expressing cosine squared of 2x in terms of the first powers of cosines. Notice that there's no exponent here on cosine. The implied exponent is 1. So that's what I'm talking about. Rewriting this something more like that. And in fact, we can express this in this form where we choose the sign appropriately. Okay, so we could do a basic substitution. We could let u be 2x. You don't have to do that, but it could help. And what's the PRI for cosine squared of u? Well, it's 1 plus cosine of twice u, that 2 is very important, all over 2, where u is 2x. Now you might be thinking, well, hey, this fraction looks uglier. It's a fraction. I have to double the argument here. Maybe, but at least it doesn't have any squares. Again, calculus hates squares. Calculus would rather deal with this right-hand side than this left-hand side. This is very easy to differentiate and integrate. And remember, sin is bad, sin is negative. The plus sign goes with the cosine or cosine squared version. All right. So cosine squared of u, if you want to do a sub, cosine squared of u is 1 plus cosine of 2u all over 2. Here I basically sub back. And what is twice 2x? What's the argument up here? In a way, that's one of the prices you pay for using the PRI. Yes, you're getting a fraction, and also you're doubling the argument. Sometimes you make it worse. But at least there are no squares here. Well, you get 1 plus cosine of 4x all over 2. Twice 2x is 4x. And really, we're done here. It was a short problem. Really, we're done here. We're expressing this in terms of the first powers of cosines, and we've simplified. So basically, this is the correct answer. But if I frame the problem like this, where I ask you to fill in the boxes and choose the sign, then you would have to go, okay, so this is going to equal, if I break up the fraction, we have 1 over 2, we have 1/2. It turns out to be a plus sign here, so you choose the plus sign. And then we basically have 1/2 cosine of 4x. A cosine of 4x over 2, that means that the 1/2 can pop out. And we have cosine of 4x. I guess I put a box here too. I might give you the 4, but the cosine of, it's a 4x over here. All right. So this is 1/2 plus 1/2 cosine of 4x. 1/2 plus 1/2 cosine of 4x. Again, we're writing this in terms of first powers of cosines, and calculus really loves to take the derivative or the integral of this thing. It can do it term by term. Okay, next up. the 8 identities that you don't have to memorize, but if I give you the appropriate block, if I give you the block of product of sum identities here, these 4, or this block of sum of product identities, these 4, then you can pick which one to use and apply it appropriately. It sounds simple, but many students actually don't get full credit on exams. They make some mistakes. First off, let's apply a product to sum identity. I want to express this product, sine of 6 theta times sine of 4 theta, as a sum. For a similar reason as for this previous problem, because calculus does not like products or quotients so much. Calculus would rather work with sums or differences because it's easier to take derivatives or integrals term by term. So calculus likes to break products up into sums or differences. Now, I'm being nice. If I give you a problem like this, then I will let you use this block of 4 identities. It might be helpful to put parentheses. Okay, pick which one to apply and apply the appropriate identity. So over here, we have sine of u times sine of v. You could even switch these. Right? Well, it turns out we want to use this first template, this first identity, sine of u, sine of v. It doesn't even matter who's who. All right, so this is the identity we apply. 1/2 times all of this, cosine of u minus v minus cosine of u plus v. By the way, it doesn't even matter who's u and who's v, because over here, of course, u plus v equals v plus u. So this guy here doesn't care which is which. But even this over here, if you put in, whether you put in 6 theta minus 4 theta or 4 theta minus 6 theta, well, they're opposites of each other. And cosine is what kind of function? It's even. So it doesn't matter if you put u minus v or its opposite, or you switch these guys, it doesn't matter. Either way, it'll work out. So it doesn't matter which guy's u, which guy's v. All right, anyway, let's apply this directly. Sine of u times sine of v, we pick this first identity here, equals 1/2 times the cosine of u minus v, that's 6 theta minus 4 theta. All that minus, well, the 1/2's in front of all this, but all of this minus cosine of u plus v. U is 6 theta, v is 4 theta, or you could have switched them. Right? Then you simplify. Some students don't bother simplifying. I do want you to combine like terms in here and in here. 6 theta minus 4 theta is 2 theta, and 6 theta plus 4 theta is 10 theta. And it turns out this would be an appropriate final answer. 1/2 the quantity, cosine of 2 theta minus cosine of 10 theta. And again, calculus has a fairly easy time differentiating or integrating this. Now, what are some mistakes that students make? Well, like I said before, students may not bother simplifying. I do want you to simplify this and this. What's a common error? Students try to combine these, almost like they're like terms or something. They're not, okay? And also, the difference of cosines is not the cosine of the difference. Okay, we don't have a factoring or distribution rule that works here. Okay, a lot of students think that this is equal to cosine of. They think, oh, 2 theta minus 10 theta is negative 8 theta. No. No, 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 no. I've just written this, but no, 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 no. Okay, that doesn't work. We don't have a rule that says that. It doesn't get much better than this. Okay, there's no way of rewriting it in a way that's really better. If you want to distribute the 1/2, that's fine, but do not do this because this here is not equivalent to this inside here. That is outright wrong. So I'm going to erase all that. Another common error, surprisingly common, people don't bother to cross their thetas. So they write 20 here, basically, and they write 100 here, and they don't bother to cross your thetas. Folks, cross your thetas. That one stroke can end up giving you full credit. Don't just leave this as an O or a 0. That's wrong. cross your thetas. I sound like eat your vegetables. Cross your thetas. It's not that hard. Boom, there you go. I'm not gonna get a ruler, okay? Boom, there you go. Okay, so cross your thetas, and again, don't try to simplify inappropriately. This is not cosine of negative 8 theta. You're not allowed to do that. Just like over here, right? Cosine of u minus v, we had a full-blown identity for that. It wasn't just cosine of u minus cosine of v. So again, that was helpful for a calculus application, like integration. How about the sum to product identities, right? Well, how about the sine of 6 theta plus the sine of 4 theta? In which case, okay, you want to look at this block of sum to product identities. You don't have to memorize these. I would give these to you. But you have to know which one to apply and be able to apply it correctly. All right, sine of 6 theta plus sine of 4 theta. Again, we can do a snap substitution if you wish. Here I use x and y. I'll call 6 theta x and 4 theta y. And again, because of commutativity, it doesn't even matter in this case, just like last time, because look at the right-hand side over here. We're going to use this first identity, sine of x plus sine of y, sine of x plus sine of y. I'm going to use this first identity, all right? We'll look over here. If you switch x and y, well, x plus y is the same as y plus x. They're equivalent, right? And again, for cosine, even though x minus y and y minus x are opposites, cosine is even, so he doesn't care. So you could switch these. But here, let's call 6 theta x and 4 theta y. And for the templates with the minus sign, it does matter who's who. Probably. Again, right off the bat, when I say simplify this, students may be tempted to rewrite this as sine of 10 theta. Oh, I want to simplify this. I'll write this as sine of 10 theta. No. Okay, don't do that. You're not allowed to do that. It's almost like they're trying to combine like terms or factor or something. Do not do that. You cannot factor out sine. You're not allowed to factor out a function. You cannot factor out sine. Sine of 6 theta plus sine of 4 theta. If you think you can do this super easily and re-express this, you're doing it the wrong way. You need this kind of identity, this right-hand side, which is not that easy. All right. So using this first identity, right? Sine of 6 theta plus sine of 4 theta, sine of x plus sine of y equals 2 sine of, x is 6 theta, y is 4 theta. I'm putting these as reminders. That's over 2. That sum is over 2 times cosine of 6 theta minus 4 theta. That's x minus y, 6 theta minus 4 theta, all over 2. Okay, work out these arguments. You have to work these out to simplify. 6 theta plus 4 theta is 10 theta. 6 theta minus 4 theta is 2 theta. We can start there. And then inside these arguments again, half of 10 theta is what? It's 5 theta. 2 theta over 2 is just theta. So we get 2 sine of 5 theta, cosine of theta. And that's about as good as you can get this if you're going to apply the sum to product identity. Now, where might you want to do this? Let's say I ask you to solve. I won't in our class, but let's say I ask you to solve this thing equals 0. Now, we don't have so much a sum method for solving equations, but we do have the 0 factor property, a factoring approach to solving these kinds of equations. So that's why it might be good to re-express this here as a product. So then you would set this equal to 0. Okay, and you would then solve this thing here equals 0. So you set sine of 5 theta equal to 0, solve that. Set cosine of theta equal to 0, solve that, and you get the full solution set. That takes some time. And I would not give you that kind of a problem on homework or exams, but you could do that. In calculus, maybe you will have to someday. It'll take some time, though. Okay. And also, you can use the identities to build up triple angle identities, like sine of 3u and so forth, in principle. All right. Next up, in our final video, for sections 5.4 and 5.5. Where do we apply these identities in calculus in a big way? That's next time.
Any questions before we go on? Any questions before we go on? Like, the next part is cool, shows you how it's used in calculus, but you won't need this for the homework. Don't go though.
Hi everyone, let's apply these identities to calculus. This is an optional section. So I'm going to claim that if f of x is sine of x, then the derivative given by f prime of x is cosine of x. The derivative of sine of x is cosine of x. And likewise, the derivative of cosine of x is the opposite of sine of x. Now remember what the derivative is. We start with slopes of secant lines indicated by this difference quotient, rise over run. You may remember this from 1.11. This was an optional section in chapter 1 about derivatives in calculus. The slope of the secant line is given by rise over run. That's the average rate of change of the function f on this interval. If we let h approach 0, if we let the run approach 0, the slopes of the secant lines will approach the slope of the tangent line in red. And that could be either from the right or the left. H could be positive or negative. We let h approach 0. And here's the limit definition of the derivative function. You'll see this in calculus. F prime of x, the derivative function rule, is the limit of this difference quotient, the slopes of these orange secant lines, as h approaches 0. If this approaches a number, that's the slope of this red tangent line, the derivative of the function at x. So basically, it's a slope function. The slope of the tangent line, the derivative at x, is kind of like the slope of the curve at this value of x. I'll show you what I mean. Let's go to Desmos. How do you graph y equals sine of x? You better know this sine wave. It's odd, and it goes to the origin. How do you graph y equals cosine of x? That's in purple. I claim to you that the derivative of sine of x is cosine of x. In other words, the cosine graph in purple gives the slopes of the tangent lines to the green graph, the sine graph. For example, I'm going to focus on the origin. The derivative of the sine function in green at x equals 0 is 1, which is the y-coordinate, the cosine value up here on the purple graph. Cosine of 0 is 1. I claim that's the slope of this green graph at the point when x is 0. In other words, I'm claiming that y equals x, which has slope 1, is going to be the tangent line to the green graph at that point. You can see that if we zoom in, this is called local linearity. Yeah, the sine graph, the sine wave basically looks like that line. It's very linear. If you have a derivative, it means you have local linearity. It means that if you zoom in on the graph at that point, you basically get a line whose slope is the derivative. I claim the slope is 1. The derivative is 1, which was the y-coordinate for the cosine graph. Cosine of 0 is 1. By the way, what's the way of seeing that? Let's look at some tangent lines, or secant lines, and how they approach the tangent line. Again, look at that green graph. Let's look at some secant lines through the origin. Through this point and this point, we have this black secant line. Through the origin and this point, we get this blue secant line. From the origin to this point, we get this green secant line. And it turns out that the secant lines will approach this tangent line. I'll put this in red, actually. All right, in red. And the slopes of the secant lines will approach the slope of the tangent line, the derivative. All right, so how do we prove that the derivative of sine of x is cosine of x? Here's the limit definition of derivative. The limit of the slopes of secant lines as h, the run, approaches 0. The run is the horizontal distance between the point of interest and the second point, which we're moving towards the first point. Okay. If f of x is sine of x, then what is f of x plus h? Think substitution. It's sine of x plus h. And how can we express sine of x plus h? we can use a sum identity to expand it. The sum of the mixed up products. And then you have some additional steps in algebra. You use some limit facts. This approaches 0. This approaches 1 as h approaches 0. You get that the derivative of sine of x is cosine of x. I would not hold you responsible for this proof. Similarly, the derivative of cosine of x is the opposite of sine of x. Let's see. Turn this off. Here's y equals the opposite of sine of x. So the cosine graph is in purple. What's the tangent line up here when x is 0? It's a horizontal tangent line. The slope is 0. That's the value for this function here when x is 0. If you plug in x equals 0, the opposite of sine of 0 is 0. So in other words, the slopes on the purple graph are given by the y coordinates on the black graph. Here, the slope is 0. Here, the slope is -1. Over here, the slope is 0, once again, and so forth. By the way, this is the first derivative of cosine of x. It's the second derivative of sine of x. The relationship is that when the second derivative is positive, this graph is concave up. So when the black graph is above the x-axis, when the second derivative is positive, the green graph is concave up. It curves upward. When the black graph, the second derivative graph, is negative, then the green graph is concave down. It curves downward. That's all calculus. It's all optional, but we needed the sum identities. You'll see much more of this in your calc class.
All right. Any questions before we go on to chapter 6? Okay, that was chapter 5 on identities, right? Simplifying. Any questions? On to the law of sines and law of cosines.
Hi, everyone. We're now going to start chapter 6 on additional topics in trig. We're going to start with section 6.1 with the law of sines. Guess what? 6.2 will be the law of cosines, and then later we'll deal with vectors. The law of sines. Know it, be able to apply it. So here's our traditional setup. We're no longer dealing with right triangles necessarily. We're dealing with more general triangles. The conventional way of labeling these side lengths and angles involve pairs of A's, B's, and C's. So we label the angle measures capital A, capital B, and capital C. And then we label the opposing side lengths as little a, little b, and little c. You can think of angle big A geometrically as eating or facing the side of length little a. Angle big B faces the side of length little b, and angle big C, which is no longer necessarily a right angle, faces or eats this side of length little c. This is no longer a hypotenuse. So these letters face or oppose each other. This triangle has 6 parts, 3 angles, and 3 side lengths. 3 angles and 3 side lengths. To solve a triangle, you're given some parts and you find the others. Here is the law of sines. How can we relate the side lengths and angles for this triangle, which does not have to be a right triangle? It goes A over sine of big A equals B over sine of big B equals C over sine of big C. We have a bunch of equations wrapped up in one line here. This equals this. Well, let's mark it. This equals this. This equals this. Also, this equals that. And of course, you can switch sides. We have several equations embedded in here. You could also take the reciprocal of all 3 parts, and you get this over here. But if you take the reciprocal of one part, you better take the reciprocal of the others. And this is all okay because the side lengths will never be 0 for a triangle, and these sine values will never be 0. I mean, sine of 0 degrees is 0. Sine of 180 degrees is 0. But you don't get those kinds of angles in a triangle. So the law of sines could be written like this or like this. Now, what must be true of all triangles? Well, an active thing we can use is the fact that, again, all the interior angles for a triangle must add up to 180 degrees. These angles ought to add up to 180 degrees. And then there's some things we could use to help check our work, broadly speaking. Let's take the triangle inequality, for example. A plus B must be greater than C, and also these must hold true. The sum of any two sides, or side lengths of a triangle, must exceed the third. So for example, A plus B must be bigger than C, and these other two must also hold. So in our picture here, A plus B must be bigger than C over here. It's basically the idea that if we wanted to get from point B to point A, any detour that we take must be longer than the straight line distance, which is represented by C here. A plus B must be greater than C because any detour, if we go from B to A, must be longer than the straight line segment going from A to B, or B to A. Detours must be longer. That's the basic idea of the triangle inequality. So A plus B must be bigger than C, B plus C must be bigger than A, and C plus A must be bigger than B. Detours must always be longer. That's the basic idea. And then the eating rule. For a given triangle, larger angles face or eat longer sides. Again, that's good as a check. So for example, if C here is the smallest angle, then little c here must be the shortest side length. If A is the middle angle in size, then little a must be the medium side length. And if B is the biggest angle, the largest angle, then little b here must be the longest side. Larger angles face or oppose longer sides, smaller angles face or oppose smaller or shorter sides. Again, that's a good way of checking your answer. For example, in a right triangle, it's true that the right angle always faced the longest side, called the hypotenuse. Examples. Let's apply the law of sines to help solve these these triangles in general. They don't have to be right triangles. Now, actually, you may just have to find one other part. You may not have to solve all the triangle, all the parts. Maybe you just have to find one part. In this case, we're going to find all the other parts. So given these three bits of information, and we can set up a model triangle. You don't need a ruler or a protractor, but do make sure that larger angles do look larger, for example. Then that'll help you check your work. So let's set up this model triangle. B is 40 degrees, C is 75 degrees. Make sure this angle looks bigger than this angle here. And little b is 23 feet. I claim that we have enough information here to be able to solve for the other parts of the triangle. All right. So how would we find angle A? Given angle B and angle C, how can we find angle A? We use the 180 rule, 180 degree rule. We subtract both of these from 180 degrees. 180 degrees minus this, we get 65 degrees. So big A here should be 65 degrees. All right. And then how can we find these various side lengths? Remember, we cannot use SOHCAHTOA anymore, at least not directly. How can we find these other side lengths? We can use the law of sines. Okay, because here's the idea. Just in general, let's use this bottom version here. Just in general, if you know any two angles, like say B and C, if you know any two angles and you know a side length, either little b or little c, that does in fact oppose one of these angles. Okay, in this case, we knew little b. Well, because we knew angle B and angle C, we could find angle A. We could find angle A. And because this is a known ratio, because this is a known value, we can then set this to either part and then solve for C here and also solve for A. So in general, if you know two angles and one of the sides opposing either angle, then we can solve the whole triangle. All right. Oh, so in this particular example, I used the top version. That's okay. All right. So we know angle B and angle C. B was 40 degrees. C was 75 degrees. And by the 180-degree rule, we found that big A was 65 degrees. So we know now all three angle measures, and we were also given little b. How do we then solve for little a? We take this known ratio. This represents a number, a constant, right? We set it equal to this first part here, and we solve for little a. And then later on, to solve for little c, we would set this equal to this, the third part. So we set this up. We solve for little a. How do we do that? How do we solve for little a? We multiply both sides by sine of 65 degrees. That's just a number. It looks kind of weird like this, but it is a number. It's a constant. Okay, so we solve this for a. We multiply both sides by sine of 65 degrees. And we get that. Exactly. A equals 23 times sine of 65 degrees over sine of 40 degrees. I'm sure on some exam, you'd be asked to approximate this. Let's say to the nearest foot, let's say. Although on a test, I hope you'll be told how to round off. Try to avoid rounding in the middle. Try not to round off before doing this. You should write this exact expression anyway. Make sure your calculator is in what mode? Make sure it's in degree mode. We tend to use degrees here in chapter 6. We get about 32 feet. And we can even label our figure here. This is about 32 feet. All right. Now we have to find little c, which should be, by the way, the longest side, because capital C appears to be the largest angle. It beats out these two guys. So this is going to be the longest side. It's going to beat 23 and 32 feet. If it doesn't, we made a mistake somewhere. All right, so how do we solve for little c? Again, we're going to take this known middle fraction and set it equal to this. Why not put the 32 feet up here? Remember, we found out that a was about 32 feet. Why not put the 32 here and set these two things equal to each other? This part, the first part, and the third part. Well, if you do that, that's not horrible. But remember, we rounded off to get the 32 feet here. You may be losing some accuracy. So you may as well take the exact value here and then use that to relate to the third part over here to find little c. All right. So to find little c, again, my various warnings, make sure your calculator is in degree mode. Make sure your calculator is in degree mode, right? Avoid approximations in the middle. Okay, so try to avoid rounding too much in the middle. Try to keep things exact as possible. And remember units, like degrees, for example, or feet. Okay, find little c. So for example, up here we had about 32 feet, right, to the nearest foot. Find little c. We set these two equal to each other. How do we solve for c over here? How do we solve for c over here? You multiply both sides by sine of 75 degrees. Okay, c equals 23 times sine of 75 degrees over sine of 40 degrees. Round that off to the nearest foot, let's say. That's about 35 feet. Okay, so let's do our final check here. Okay. Well, these three angles should add up to 180 degrees. We really made that so early on. The triangle inequality, I'll circle the side lengths in red. We have 32, well, maybe not red. How about purple? We have 23 feet here, about 32 feet here, about 35 feet over here. All right, the triangle inequality, detours are always longer. 32 plus 23 is greater than 35 in feet. 23 plus 35 is greater than 32. 35 plus 32 is greater than 23. All detours are longer than the straight line distance. So the triangle inequality is satisfied. Also the eating rule. The smallest angle, the 40-degree angle, faces the shortest side, 23 feet. The medium angle, 65 degrees, faces the medium side, about 32 feet. And the largest angle, 75 degrees, faces the longest side, about 35 feet. So these are good checks. They're not perfect checks, but we feel pretty good about this answer. It at least makes common sense. Okay, so all the parts we found, they're in blue here. Hi, everyone. Continuing with 6.1 on Law of Sine.
Okay, any questions? Now, actually, this video here is optional, describing cases like the ambiguous case. We're actually going to skip this one. You can view it at your leisure. We're going to skip this video, actually.
That is required, and that's next time.
Well, the next thing is required.
Hi, everyone. We're now going to develop 3 sine formulas for the area of a triangle. And actually, we're going to be able to compute the area using these formulas in the SAS case, meaning that we know 2 side lengths of a triangle and the included angle between them. For example, side lengths little a and little b, and angle measure big C. So we have all 3 letters involved here. The area is equal to 1/2 AB sine of big C. You can think of it as half the product. I'll circle this. You can think of it as half the product of 2 sides and the sine of the included angle between them. And this represents the 3rd letter. You need to have all 3 letter types, an A, a B, and a C. Well, likewise, and the proof that I'm going to show you can be altered in corresponding ways, but you can show that the area also equals 1/2 BC sine big A. That's if you know little b, little c, and big A. Also 1/2 little a, little c times sine of big B. So again, if you know 2 side lengths and the included angle between them, all 3 of these area formulas will work for acute, right, and obtuse triangles. In fact, what if C is a right angle? Let's talk about that. What if C is a right angle? If C is a right angle, right? Well, sine of C, sine of 90 degrees is what? Sine of 90 degrees is 1. Remember, S-I-N. Right? Sine of 90 degrees is 1. Right? And then you get area equals 1/2 AB. Here's little c, here's little, well, okay, oh, here's little a, and here's little b. Wait, 1/2 AB, that's 1/2 height times base, or base times height. Yeah, makes sense. So it works for a right triangle. That's a special case. Okay, so all 3 of these work. Now I'm going to show you something really cool. Well, first of all, let's do a proof. I'm going to prove this for you. Okay, and the ideas of the proof. So we're going to get to that, all right? And we're going to see why it's in this section. All right, so let's talk about the proof of this. Let's take this model triangle, all right? Well, again, the area of a triangle in general is, in your old geometry class, 1/2 base times height. And fortunately, we're going to be able to use B here as our base. So 1/2 base times height. The problem is H is not given to us. We have to find it. I'm giving you the things in purple, little a, little b, and big C. SAS information. Well, let's look at this triangle in red. This triangle in red here. I know little a, I know big C, I want little h in blue. So I'd like to relate an angle, the opposite side, and hypotenuse. Sine does that. Sine of C is opposite over hypotenuse, h over a. Remember, h is height, not hypotenuse. A is the hypotenuse. Solve for h, multiply by a on both sides, and h equals a sine of cap C. So area is 1/2, base is b, height is h. What's h? It's a sine of c. Right here, a sine of c, plug that in. I can switch these. 1/2 ab sine c. And you can get the other two formulas by making another side the base. You can make a the base, or you can make c the base. It's a similar analogous analysis. All right, now I'm going to show you something really cool. So we have these three formulas for the area of a triangle in terms of the sine function. I'm going to equate these formulas for the area. Let's multiply all three parts here by 2. So we basically cut out the 1/2. And what do you think I'm going to do next? Take a look here. We're going to divide by something. In fact, 3 things. We're going to divide by A, B, and C on all 3 parts. Take a good look at this. What happens? And what do you get? I'll show you the cancellations. AB over AB is 1. BC over BC is 1. AC over AC is 1. If you move this over here, you get the law of sines. That's a proof. Next time, the law of cosines.
I always think that proof's really cool, don't you think? Okay, because you get to see it, then you own it, as Professor Marquez would say. All right, going on to the law of cosines. Any questions? Any questions?
Hi, everyone. Let's do section 6.2 on the law of cosines. And again, I'll be nice. I'll tell you when you can use the law of cosines, although later instructors may expect you to know when you can use it. The same setup as before. You have the letters facing each other. Little a faces or opposes big A. B faces B, C faces C, and so forth. Well, here's the bottom line. You have to remember this formula. It should look very familiar. C squared equals A squared plus B squared. That smells like whom? That smells like Mr. Pythagoras, and there's a reason for that. And then this fudge term, minus 2AB cosine of cap C. Now, what happens if capital C is a right angle? Okay, so what if we do have a right triangle where we make capital C the right angle? Well, then what's the cosine of 90 degrees? Remember, COS, or the x coordinate up here. What's the cosine of 90 degrees? It is 0. So this term completely dies, and we get, lo and behold, the Pythagorean theorem, right? Here's little c, here's little a, here's little b. C squared equals a squared plus b squared. So in the case where capital C is a right angle, and this is really a hypotenuse, then we have our classic Pythagorean theorem. In fact, you can think of the law of cosines as a generalization of the Pythagorean theorem. This generalizes the Pythagorean theorem to all triangles. The Pythagorean theorem only applies to right triangles, where you have a right angle and a hypotenuse. But the law of cosines generalizes the Pythagorean theorem to all triangles, like this guy. Or you could think of the Pythagorean theorem as a special case. The Pythagorean theorem is a special case of the law of cosines over here. But the law of cosines is like the Pythagorean theorem for all triangles, not just right triangles. So for memorization purposes, sure, the Pythagorean theorem helps. This looks like the Pythagorean theorem, except there's a third term, this fudge term here, which accounts for the fact that capital C may not be a right angle. The further away this is away from a right angle, then the more of an impact this fudge term is going to have. So we get that the square of one side equals the sum of the squares of the other two sides minus twice the product of these sides, okay, times the cosine of the angle between them. This letter is the capital version of this letter. A and B are symmetric here in the sense that I don't care which leg is A and which leg is B. By the way, these are not legs if it's not a right triangle. But basically, the idea is that C is one side, and you know, if it's not a right triangle, then C is not even the hypotenuse. There's nothing special necessarily about little c. But c squared will equal a squared plus b squared minus twice the product times the cosine of the angle facing the side of interest. Again, A and B are symmetric in the sense that you can switch these and it won't matter. So basically, if C goes from a right angle and shrinks down to an acute angle, little c will be smaller. And you can see that in the formula. If the angle is acute, then you're subtracting a positive value, and then c squared, and therefore c will shrink as we go from here to here. But if the right angle expands to an obtuse angle, then the hypotenuse gets longer. The hypotenuse becomes a longer side. If c is obtuse, then the cosine is negative, which means that the fudge term is positive because you have the minus sign there. C squared grows, therefore c grows. So you can do a thought experiment, and you can see why this minus sign makes sense. Of course, in the case of a right angle for capital C, this is 0. We get the Pythagorean theorem. But this all makes sense. Now, by using a similar proof, you basically have a similar pattern here. There's a certain symmetry among these formulas. So again, a squared, the square of one side, equals the sum of the squares of the other two sides minus twice the product of these side lengths times the cosine of the angle between them. This letter is the capital version of this letter on the left. Again, over here, b squared equals a squared plus c squared, the sum of the squares of the other two side lengths minus twice the product of the side lengths times the cosine of the angle between them. This is the included side for A and C, but it opposes this side. Looking at our setup, okay, looking like over here. In fact, I'll go way back here. I'll go way back to the original one that we focused on, right? Going back to this guy over here, remember that capital C faces little c. And is the included angle between these other two side lengths. All right. So again, over here, b squared equals the sum of the squares of the other two side lengths minus twice those lengths times the cosine of the angle included between them, which faces the side or the side squared of interest on the left. Now, you could solve for, up here, you could solve for cosine of cap C. Down here, you could solve for cosine of cap A and cosine of cap B, and you can get these variations. So you could say there are 6 or 9 laws of cosines, but they all ultimately come from memorizing this. If you can memorize this, then you basically know the law of cosines. Again, you follow similar patterns to get the other two versions for a squared and b squared. And let's say that you're curious to find c. Well, you can find c very quickly if you have SAS information, meaning that you know two side lengths and the angle included between them. So for this formula, if you know two side lengths and the included angle, you can plug this information into the right-hand side. You can quickly get c squared and then c. Now, when you solve for a cosine of the angle, and you get these three variations, then these are ideal for SSS setups, where you're given three side lengths for a triangle. Then you plug in those side lengths. This side faces this angle of interest here. You can find these cosine values. By the way, I'm assuming that the three side lengths you're given will work. They will form the side lengths of a triangle. They will satisfy, for example, the triangle inequality. If I give you three pickup sticks, one is 3 meters long, one is 4 meters long, and one is 10 meters long. Can you form a triangle where you put these pickup sticks corner to corner? Nope, you cannot get a triangle because you're going to fail the triangle inequality. The detour would have to be longer than the straight line distance. Basically, these two sides won't be able to meet. Okay, a detour is never longer. Sorry, a detour is never shorter. A detour is never shorter than the third side. A detour has to be longer. 7 meters won't cut it. 7 meters, that's too short of a detour. That's shorter than the straight line length. Anyway, if you have appropriate SSS information, you can find the cosine of the angle. And in fact, if you're willing to use the inverse cosine notation, you can even come up with three more variations. Capitals from here, okay, cosine of cap C is all this. You could say that cap C is the inverse cosine of this, or arc cosine of this. Although books tend not to write this out. And you might ask, why not? I mean, you actually have this formula solved for an angle, like the angle for C, the measure of angle C. But here's the thing. Technically, books say that when you have an inverse sine, an inverse cosine, or an inverse tangent, the output should technically be measured in radians. And I think one reason why some textbooks don't write these variations is because we deal so often with degrees. Textbooks don't like to put this notation if we're going to write our answer in degree form. Personally, I don't have a problem with that. So even though we're going to give the angle measures in degree measures, typically in this chapter, I'm okay with using this inverse cosine notation, even though books normally expect a radian measure for output. I say degrees are okay. It's okay to work out an inverse cosine expression and you give the answer to me in degree form, provided you indicate the degree symbol. So there are 9 variations. But again, you really just have to memorize the very first one. So again, the logic, memorize the very first one. It looks a lot like the Pythagorean theorem, but there's a fudge term over here. And then from symbolic symmetry, you can get the other 2 versions for a squared and b squared. Don't forget to take the square root if you want c, a, or b. And then you solve for these cosine expressions. You can do it algebraically. You don't have to memorize to get these versions. And you can use the inverse cosine versions to get the last 3. So there are 9 versions of the law of cosines, but it all comes down to memorizing one and maybe doing some algebra. And again, the same checks work. Well, we can use the fact that angles have to add up to 180 degrees, and all of the angles have to be strictly between 0 degrees and 180 degrees. Again, they add up to 180 degrees. The triangle inequality has to apply. Detours are never shorter, they have to be longer. And the eating rule has to apply. And again, the law of cosines, okay, they apply very well in the SSS case and the SAS case. So if you know 3 side lengths, then these versions are good. Then you can find the cosines of angles or the angles pretty quickly. And if you have SAS information, you can use formulas like these, including the Big Daddy, the C-square version. If you're given 2 side lengths and the included angle between them, which has the same letter as this guy. Now, once you know the games involved here, right, all these games here, then the examples are very straightforward. So in the SAS case, I give you 2 side lengths and the included angle between them. So all 3 letters are represented. We can solve the triangle. So I'm giving you the pieces in black, 2 side lengths and the included angle. So SAS, I'm giving you SAS information. Find the other parts. I just have one angle. I can't use the 180-degree rule yet for the sum, but we can find the third side length, for example, by using the law of cosines. B squared, here's the unknown, B squared equals the sum of the squares of the other 2 sides, so A squared plus B squared minus twice AC times the cosine of big B. Plug in, make sure you're in degree mode, and do not combine these right off the bat. A lot of students love to do that because they love to combine integers. Do not combine those. Remember, the cosine of 70 degrees attaches to these, and we have a single term inside the radicand here. Do not bring these in. Do not combine these in with this. These coefficients apply to the cosine value. So these should not be touching these over here. You get about 7.08 centimeters. You might want to keep the whole version in your calculator in memory. But to 2 decimal places, to the nearest hundredth of a centimeter, B is about 7.08 centimeters. Maybe I should type it. B is about 7.08 centimeters. Again, you may want the more full version on your calculator in memory. It's not exact, but you'll get a better approximation on your calculator. Again, do not combine these. Do not blend these together. These guys go with him. All right. And then you can use the SSS versions. Since we have the 3 side lengths, you might want the better approximation for B. So use for what's in your calculator. Books might suggest blending in the law of sines, but I think that's confusing. I think it's more straightforward to just go straight with the law of cosines, even though it might be a bit more work. All right, work this out. Make sure to process the numerator before dividing. And it's a triple division. You're dividing by all 3 of these. So either take the product first, or remember, it's a triple division. It's the numerator divided by this and this and this. It's a triple division. You might not want to round off. You might want to keep the full entry in your calculator display, all the digits. Okay, cosine of A is all that. So the inverse cosine, A is the inverse cosine of all this, right? A is the inverse cosine of all that. A is about 41.6 degrees. So this here is about 41.6 degrees, about. All right, and then now, how do we find angle C? We're given this. We now have this over here. We can use the 180 rule. 180 degrees minus that, about 68.4 degrees. It's easy to find that third angle once you find the other 2. We're given one, and we found a second one. All right, so some quick checks here. Well, we made it so these added up to 180 degrees. You could double check that these add up to basically 180 degrees, up to rounding error. How about the triangle inequality? Well, this plus this is greater than 5 centimeters. This plus this is greater than that thing. This plus this is greater than that. So all the detours are longer. And also the eating rule. The smallest angle, capital A, faces the shortest side, 5 centimeters. The medium angle, capital C, okay, faces this medium side length, 7 centimeters. The largest angle faces the longest side, about 7.08 centimeters. But notice that we almost have an isosceles triangle. These degree measures are very close, so it makes sense that these side lengths are very close because it's almost an isosceles triangle. Some good checks there to make sure our answer makes common sense. For the SSS case, well, for two of the angles, you can use formulas for cosine of C and cosine of A, and you want the inverse cosine function to be able to figure out C and A. Plug in, you get these angles. How do we get the third angle? The 180-degree rule. Because remember, I'm giving you 3 side lengths. I'm not giving you any angles, but you can find 2 of the angles using variations on the law of cosines, and then you can find the third easily. Next up, a few comments about area formulas, optional. Hi, everyone. Here's a...
Okay, now this is optional, but it's really cool. So hang on for this. Any questions? Any questions? This is really cool, actually.
Cool but optional video about the area of a triangle. It's Heron's formula. And this is proven using both the sine formulas from 6.1 and also the law of cosines. That's why it's here. How do you find the area of a triangle if you're given 3 side lengths? Assuming they satisfy the triangle inequality. You can't have 3 meters, 4 meters, and 10 meters, for example. If that happens, then, for example, here you might get a cosine value equaling 2, for example. All right, so they have to satisfy the triangle inequality, meaning that every detour has to be longer. Okay. Now for Heron's formula, remember the SAS, if you have SAS information, you can use the 6.1 sine formulas. If you're given 3 side lengths, it turns out this formula works for the area. I won't go over the proof, but its structure is very interesting. The area is given by the square root of, and by the way, you might want to use area instead of A because A might just represent angle. All right, so area equals the square root of S. S is the semi-perimeter. It's half the distance around the triangle. It's half the total sum of the side lengths. It's the semi-perimeter times these factors, S minus A, S minus B, and S minus C, where A, B, and C are the side lengths. So that's a cool formula to apply. Notice it's symmetric in A, B, and C. I don't care how you label these. I could permute these and you'll get an equivalent expression. You can switch these factors around. Incidentally, if the triangle inequality is failed, if I give you pickup sticks of length 3 meters, 4 meters, and 10 meters, then you're going to get a negative in here. And this thing will blow up, basically. But here, you have an expression for the area of a triangle in terms of basically the side lengths. Pretty cool. All right.
Okay, so that's that for today. All right. So are there any? And I'll stick around for questions, though. I'll stick around for questions. Okay, so we're at 9:24. That's it for the videos. But remember, I had these on previous YouTube videos, including an office-hour video from Monday with most of these. 512B was, I think, after class Thursday, perhaps sometime last week, at the end of my class video, right? Okay. So that's all new for today. In the meantime, I will take questions. So go ahead and chat at me. Let's just get set up here. All right, any general questions or general or specific questions? General or specific questions? Let's see, questions, general or specific. Okay. All right, so feel free to go ahead and put in problems in the chat if you wish, or speak them to me, all right? Remember, I do have some available on videos, all right? Okay, so let's do this. Get out the tablet here. All right, so let's now go straight to the questions. All right, homework 4. Well, for my old midterm 4, I should say. It's your 5th assignment. Okay, so 531N is the first request I see. Ah, yes, lots going on there. All right, so grab, let's see here. All right, on screen. All right. So again, I'll do a mix of typing, mouse, tablet. Okay, now over here we're doing 5.3.1n. All right, and let me know if I make a mistake anywhere. All right, go to let's say blue. All right, so this one here. All right. Now, you don't have to recopy the original, but I think for you as a student, if you have time, go ahead and recopy the original for your benefit. But so we start here, all right, and we're first going to use the fact that cosine is even. All right. Cosine is even, which means we can do what with this opposite sign here? We can zap it. All right. I'll go ahead and write this out. All right. So when we do that, we're going to get, okay. So let's go to here, 2 cosine cubed of x. Whoa, whoa, whoa. I lost all that. Gotta be careful what I press. Let me, all right, let me start over again. Gotta be careful what I press. Okay, 5, 3, 1n. 5, 3, 1n. All right. Okay. Careful. 2 cosine cubed of x plus sine. Whoops. Sine. Squared of x equals 1 plus cosine is even cosine of x. All right, because cosine is even once again. All right, so that's the easy part. We have a long way to go. All right, I better keep saving just in case. Okay, now next up, like the old children's shows, one of these things is not like the others. One of these things is not like the others. All right. Okay, so sine squared of x, we're going to make it look like the others. Well, how can I make sine squared x look more like cosine squared x? Once again, we've seen him before, Mr. Pythagoras. The Pythagorean identity. I want to make this look more like the others. So what I'm going to do is, I'll go ahead and write the new line here. All right, so so we have 2. Oops, go to blue. All right, so we have 2. By the way, I'm still recording, right? Yes, I'm still recording. But let me know if you want me to stop recording. This is very helpful to the class, though. 2 cosine cubed of x. Whoa, whoa. Two cosine cubed of x, all right, plus the quantity 1 minus cosine squared of x. I have that in parentheses right now, but since there's a plus sign out there, not a minus sign, they're not so necessary. Okay, so because there's a plus sign here, I don't need these. But be careful. If that were a minus sign, I would need these, or I'd suggest them. Otherwise, you have to distribute. Okay, equals 1 plus cosine of x. All right. So, let me note something right now. All right. Okay, let's see. Okay, now we could substitute. It might be easier on, well, it might be easier on the eyes to do this. First of all, notice we have a positive 1 here, positive 1 here. We can subtract 1 on both sides. And these basically knock out. Over here and over here. All right. Now go over here. We have 2 cosine cubed of x. I still have minus cosine squared x. And you see I'm going to subtract cosine of x on both sides. Okay, subtract cosine of x of on both sides. All right, is everyone okay? Is everyone okay? Just checking up. Any questions up until this point? We've done a fair bit. We've used the even property for cosine, right? We've used the even property for cosine. We've used the Pythagorean identity to express sine squared x, so it looks more like the others. Sine squared x is 1 minus cosine squared x. To be safe, be prepared to put grouping symbols, but since that's a plus sign, not a minus sign, I can go ahead and scratch these out. But again, if that were a minus sign, you have to be more careful. Subtract 1 for both sides. That basically cuts out the 1 over here, the 1 over there. Good, good. All right. Now at this point, now you don't have to substitute. You rarely have to substitute. But here, let's go and do a substitution, if that's okay, unless you insist otherwise. I'll do this in, how about purple? Purple. All right. Okay, so, well, I could have just typed it in. Let u equal cosine of x. Let u equal cosine of x. All right. Okay. So we have 2 u cubed minus u squared minus u equals 0. Okay. Now, technically, if you write this out on paper, you should line up the equal signs. I would never mark down for that, but if you can, try to align the equal signs. Okay, that's good practice. Okay, I admit here I'm being a bit hypocritical. I'm just trying to get through this. All right. But so are you folks, I guess. All right, now we factor out the GCF. The GCF is u. All right, factor that out. And then these exponents decrease by 1. U to the 0 is 1. So we have u squared minus u minus 1, all right, equals 0, right? U divided by u is 1. And we have the minus sign in front still. All right. And then we can factor this old school. You could use the quadratic formula. We want the zeros anyway, but this does factor old school. Oh, I forgot the 2 in front. Maybe this didn't factor old school. This factors old school. Got to put the 2 in front. Also focused on the powers of u, forgot the 2 there. All right, now this cutie, you can factor old school. Okay, you need the 2 there. All right, assuming it works, 2u over here, u over here. Let me see if I can move this up a little bit. There we go. All right, we need split signs, but we need a heavy negative. So negative 2u plus 1u is negative 1u. All right. So we, whoa, that's a 1 there, positive 1. Okay, so a question so far. We're doing old school factorization over the integers. Old school factorization over the integers, right? 2u squared minus u minus 1. That cutie, that quadratic trinomial, factors as 2u plus 1 and u minus 1. 2u squared minus 2u plus 1u, that's negative 1u. Positive 1 times negative 1 is negative 1. Again, you could use the quadratic formula. That's page 1. That's page 1. Any questions before I go on to page 2? Let's do page 2. All right. Let's proceed. Okay, so now we're going to use the zero factor property. We have 3 cases. U equals 0, 2u plus 1 equals 0, and u minus 1 equals 0. All right. And then I can solve these all for u. Subtract 1. All right, so subtract 1 from both sides, divide by 2. U equals negative 1/2. I'll start with these for now. We have u equals 0, u equals negative 1/2, and add 1 to both sides, u equals 1. All right. And then we're going to go through these 3 cases. Case 1, u is 0, u is cosine of x, right? U is cosine of x. We have cosine of x equals 0. Oops. Okay. And I'm basically going to replace u now with cosine of x. Are there any questions so far? Questions about my factorization, right? Factoring this polynomial in u over the integers, and then I go back. U is cosine of x, and I'm now doing the trig phase. Any questions thus far? Any questions thus far from anyone? Any questions so far? All right, very good. Okay. No, although if you have questions, please let me know. All right, so cosine of x equals 0. As I said, 3 cases, right? U goes back to cosine of x. We also have cosine of x equals negative 1/2. Technically, it's an or, right? Or cosine of x equals 1. So 3 cases, all involving small equations with cosine of x. And then now I'd encourage you to look at the unit circle, especially for quadrantal angles, because tables aren't as nice for quadrantal angles. All right. I won't put units or anything, but okay, cosine of x equals 0. Now, x actually is the angle here, right? Technically, x is the angle here. Cosine of x is the x coordinate. Okay, so cosine of x, this here, is really the x coordinate on the circle. Okay, technically, x is the angle. Cosine of x is the x or horizontal coordinate on the circle. Well, where's cosine of x equal to 0? Where is the horizontal coordinate equal to 0? At the North Pole and the South Pole. All right. Now, we could wait and see what we get from here, but we could try to characterize this now. All right, so let's say we want to solve this mini equation right now, okay? So what would the solutions here be? X equals, what is the famous angle we often associate with the North Pole? How many radians? Pi over 2, very good, okay? And then to get each solution, you're going to revolve by half revolutions. How many radians are in a half revolution? A full radiation, yes, a full revolution is 2 pi, so half a revolution would be pi. All right, so plus pi n, where n is integer. All right, any questions about that? Okay, any questions about that mini equation? All right. Now I'm going to put this in a step builder form later. And again, if you think there might be some really great symmetries, you might want to wait before writing these things out. But I don't think we'll get a really great one here. Maybe some, but not really super great symmetry. I don't think a one thing deal here will work. All right. Question so far. Question so far. This is good. Okay, we're good with equation 1. Questions? All right. Now, looking at equation 2. All right. For consistency, I'll use green again. Okay, don't make it too wild. All right. Again, we're thinking x coordinate. Now, in what two quadrants will the x coordinate on the circle, will the cosine value be negative? In which two quadrants will cosine be negative? Quadrants 2 and 3. Very good. Or you could try to draw the points. Notice that if this is a famous value, but the magnitude, the absolute value of 1/2, that means that they're fairly close to the axis. So these are the steep angles, not the flatter angles. All right. Okay, now what famous angle do we normally associate with this point here? It's kind of high here. Now, his brother, his reference angle here, the reference angle to these solutions is the high steep angle, pi over 3, right? But that's not a solution to this. We want brothers. We want brothers. Do you know the famous brother in quadrant 2? It's what pi over 3? Do you remember? Very good, 2 pi over 3. The common trick is that if you have the reference angle here, like pi over 3, the trick is in quadrant 2, notice that 2 is 1 less than 3. It's pi minus pi over 3. Very good. All right. Now, if you want, you could associate this point here with 4 pi over 3. But remember, you can also associate it with negative 2 pi over 3. Okay, if you reverse and go clockwise, right? Here's positive 2 pi over 3, and here's negative 2 pi over 3. So if I want all real solutions, okay, I believe I want all real solutions and also the ones between 0 and 2 pi, right? So I think both of these could be helpful. All right. But in the meantime, if I want the solution set for this little guy, all right, x equals, how about plus or minus 2 pi over 3 plus 2 pi n, because I need full revolutions to get the coterminal angles, plus 2 pi n. Where n is integer, maybe I'll drag this to the very end. Questions so far? All right. Questions so far? Okay. Any questions? Any questions? We've done these two little equations. All right. Let's now proceed to the third equation. All right. Cosine of x equals 1. What point does that correspond to? The cosine of x is the angle x is the angle here. Cosine of x is the x or horizontal coordinate on the circle. Okay, right. Over here, which we associate with 0. All right. Okay, so we have here x equals, a lot of students put 0 plus, but you don't have to put 0 plus. You can just put 2 pi n, right? Because we start at 0, and then we add 2 pi n, indicating 4 revolutions. So far, so good? All right. So in terms of all real solutions, I could spruce this up a bit. For all real solutions, basically, I'm going to squeeze this in. The set of all x in the reals such that you have this, or this, or this, where n is integer. That's the roadmap. And let me check quickly to make sure that is correct. One moment. Let me make sure this is correct. Whoop. Okay, n. Yes, this looks good. Now, there are various ways you could write this. Oops. All right, the set of all x in the reals, such that, this is nice, nice typeset. The set of all x in the reals, such that x equals pi over 2 plus pi n, or x equals, I put this at the end here. Doesn't matter. X equals plus or minus 2 pi over 3 plus 2 pi n, or x equals 2 pi n. I don't care if you switch these, where n is integer. Okay, so if you write all that down, you're in good shape. Any questions about the general solution? Any questions about the general solution? No, thank you. All right. Now, and then there's another question. What are the solutions between 0 and 2 pi, right? Then you want to go around the world. Okay. Well, just kind of look at the pictures here. We don't need a single picture, though sometimes it helps. So over here, you can see we pick up 0. As we walk around, we get the 2. I'll circle them. We get the 0. And then we walk around, we get the 2 pi over 3 and the pi over 2. Okay, so we have pi over 2, and then 2 pi over 3, and then 4 pi over 3 over here. Remember, we want non-negative angles. And then over here we have 3 pi over 2. Observe that this quadrantal angle is 3 pi over 2. Okay, and that's it because you don't go back to 2 pi. I put a parenthesis at the 2 pi. So yeah, that's it. 0, pi over 2, 2 pi over 3, 4 pi over 3, and 3 pi over 2. Bear in mind that you do not have to order your solutions in the solution set. So you can mix up the order. Like you could do this, 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 that. Sets are unordered, so you don't have to sort them. All right. Okay, any questions from anybody? Any questions? Okay, any questions before I save my work? All right, so let's save this. Yes, you're welcome. By the way, sometimes there's a private chat. So in case if I'm talking, if it seems like I'm talking to myself, no, I'm probably talking to someone who's chatting privately. All right. Okay, so we had another one up here. Oh, let me put this away for now. Now I'm saving these. So if you want me to refer back to this, let me know. And I'm glad I'm saving these. Look at all this work. I'm glad I'm saving those. Also for the students, right? Okay, so there's another one up here. Yes, a couple, right? 521C. All right, so let me go back to 521C. Oh, okay, now this one. Oh, okay, so here's the deal. On this one, I went over this with a student, I think earlier to, oh, no. I think I did it, wait, let me see here. Yeah, 521C. Now, I have a video recording of that for my office hour. Now, what I can do is, I do have a record of it. So maybe we can do this kind of quickly at least, and then you can refer back to the video. But let me get the notes I had on that. I'm glad I saved these. Yeah, 521C. All right, so we'll leave you in some suspense. All right, but I have this written out. Okay, so I at least have this written out. And let me know if you need me to elaborate. But let me go through this. All right, again, I do have another recording in the videos, but the left-hand side, you should indicate where you're starting. Okay, tangent is odd, right? So this opposite sign pops out, makes it plus. For some students, it helps to write this over 1. All right. Now, on the right side, we just have one term. So I think it would help me to build up this fraction, get tangent of alpha as a common denominator. So I multiply by 1 in the form of tangent of alpha over tangent of alpha. Okay, get a common denominator. Okay, so we get 1 over tangent of alpha plus, well, tangent of alpha times itself is tangent squared of alpha over 1 times tangent of alpha is tangent of alpha. All right. Okay, now the goal is to get a common denominator. Let's add the fractions. We add the tops. We get 1 plus tangent squared of alpha all over tangent of alpha. Now don't give up yet, because you should recognize this. Hey, the square of a trig function a 1, we might be sniffing out what identity? What identity? Turns out to be Mr. Pythagoras, the Pythagorean identity. 1 plus tangent squared of alpha is secant squared of alpha. And if you forgot that, then you can write these notes over here. You have to remember the big daddy, right? Sine squared of alpha plus cosine squared of alpha equals 1. We think this is secant squared alpha. You can try it by dividing both sides by cosine squared alpha, right? Now, if this were a verification, I want you to show breaking up the fraction, but maybe you can do this mentally. Sine squared alpha over cosine squared alpha is tangent squared alpha, plus cosine squared alpha over cosine squared alpha is 1, equals 1 over cosine squared alpha is secant squared alpha. That's the top. Now, I'm kind of skimming over this. Again, I have the video up, but I will ask if there are any questions. Right. Any questions? Any questions? Any questions? Any questions? All right. Now, my strategy here, this might seem a little strange, but since secant alpha is part of my target, my strategy here, you might do it differently. I took one of these and peeled it out, put it on the side, right? I'm left with just regular secant of alpha, right, over tangent of alpha. And then I might resort to going to sine and cosine, right, because I'm trying to get this to be cosecant of alpha. So I use the reciprocal and quotient identities. It turns out the little cosine of alphas do cancel because you can multiply by cosine of alpha over cosine of alpha. Or, as I do in page 2, when you divide by something non-zero, you're multiplying by its reciprocal. Okay. In any case, you end up with 1 over sine of alpha. 1 over sine of alpha times secant of alpha. Is 1 over sine of alpha cosecant of alpha? Yes, it is. The QED is optional. That's just a fancy way of saying end of proof. All right. Questions? Questions? Any questions? Anybody? Any questions on this? Any questions? All right. So again, I have this here, and it's also on the video from Monday. All right. Another question was. Okay, good. There's a 512A. Is that another one that? Yes, 512A is another one that is in the Monday YouTube video. But again, I have the notes from that. I've saved them. All right. I got to remember, these are helpful. 512A right here. Okay. In fact, I discussed this today with a student. All right. So we start with this left side. I note that secant and cosine are both even. All right. So I can knock out these opposite signs here. All right. On the top, 1 minus secant of x. All over on the bottom, 1 minus cosine of x. So we don't need we can delete the opposite signs there. All right. Now, this is a simplification problem. I don't have a target. All right. So I decided to break this up in terms of sine and cosine. Secant of x by the reciprocal identity is 1 over cosine of x. Okay. Well, that's one of the reciprocal identities. All right. And then on the bottom, 1 minus cosine of x. So my strategy is that I have to deal with this compound fraction. So I decided to multiply by 1 in a nice way. Let's multiply by cosine of x over cosine of x. Why? So I can get rid of that little denominator there. But remember, cosine of x distributes through the top. Now, the fraction bar automatically groups the top and the bottom, but it's good. I think it's good for students to put the grouping symbols. I think that does help, to have the brackets here and the brackets here. I think that does help. Okay. Thank you all. Yes. Okay. So on the top, we're going to distribute. All right. 1 times cosine of x is cosine of x. I do the distribution over here. the distribution is not in the video. This is in today's office hour, this piece. Minus, okay, 1 over cosine of x times cosine of x. Well, these knock out and you're left with 1. So we have cosine of x minus 1 all over. Now, many students want to distribute here because they like to show off. Don't, because we like factored forms. The problem with the guy on top was that we had a fraction as part of this, right? We had a fraction inside of this overall fraction. So we wanted to distribute the cosine of x. There are no fractions inside the bottom, so I might be better off leaving this in factored form. Otherwise, we may have to just factor back later on. You don't want to waste your work, waste your time. So I'm going to keep that in factored form down here. And then a key observation is, look, here, if you imagine a snap substitution, if you let y be cosine of x, for example, how do you divide y minus 1 by 1 minus y? Basically, what's this? Well, how is y minus 1 related to 1 minus y? They are opposites. And what happens when you divide a pair of opposites that are not 0? Like, for example, what is 5 divided by negative 5? It is negative 1. All right, so I can cross these out. I get negative 1. Let's say on the top, we have a 1. This, right, when you divide these, you get negative 1 on top, 1 here, and also the cosine of x, right? So we end up with the opposite of 1 over cosine of x. Now, when we say simplify, we generally mean make things more compact. So in the end, I don't want you to leave it as opposite 1 over cosine of x. I want you to write it as the opposite of secant of x. Again, this video is also explained. This is also explained as part of the Monday office hour video in the YouTube playlist. All right. Okay, so I think I hit the questions in chat. Are there any other questions at this time? Any other questions at this time? Questions? Otherwise, I'll wait until 10 sharp. I'll come back and see if there are more questions. So if you wish, good night, but I'll come back at 10 p.m. to see if any more questions. Like in a minute.